Welcome all of you. In the last couple of classes, we discussed extensively analysis of the proton NMR spectra. We took various examples starting from simple molecule, a CH2D2. We simulated the spectra for different nuclei. Then we went to the real spectrum of molecules, right, starting from small molecules, simple spectra, and went up to little bit complex spectra. We knew how to analyze the spectra based on chemical shift, multiplicity pattern, and also intensity of the peaks. We understood all those things. Also, we looked at the spectra of molecules containing phenyl groups, and I explained to you about the multiplicity pattern that one expects in phenyl groups depending upon the substitution, whether it is a monosubstituted, disubstituted, symmetrically, asymmetrically disubstituted, ortho, meta, para substitution. Various examples we took, and I showed you how multiplicity pattern can be explained based on the substitution at the place where substituents are present in the phenyl ring. Subsequently, we also analyzed varieties of spectra where we could determine heteronuclear coupling between proton and the abundant species like fluorine and phosphorus. Not only single heteronuclear, sometimes two heteronuclear both present. We extended further and we wanted to get the spectrum of molecules where some of the nuclei like carbon-13 and nitrogen-15 are present in the natural abundance. Such molecules will give rise to satellite spectra when protons are coupled to dilute species like carbon-13, nitrogen-15, silicon, selenium, etc. And we could take a large number of such examples, and we also analyze such spectra, and we knew how we can get the heteronuclear couplings from the satellite spectrum. Further, in some symmetric molecules where the protons are chemically equivalent, couplings are not reflected in the spectrum, in which case we wanted to get the coupling from the satellite spectrum. I also took an example, not one, several examples of how the proton-proton couplings are reflected in the satellite spectrum. So, analysis of the satellite spectrum also gives you not only heteronuclear coupling, but also proton-proton couplings. And we also extended further, and we wanted to see what will happen when we have a magnetically equivalent spins, whether we are going to get the couplings. We do not get the couplings, especially when the spins are magnetically equivalent. How do we get that? By what is called the isotopic substitution. I showed you how we can do isotopic substitution. For example, replacing proton by deuterium, we get the heteronuclear coupling proton and deuterium. If I know JHD, then I can calculate JHH by knowing the ratio of the gamma of proton or gamma of deuterium. This I explained to you, and it is very easy in magnetically equivalent spins. When the couplings are not reflected in the spectrum, this is the way we can get the coupling by isotopic substitutions. So, I explained all those things. Now, extensively we analyzed proton NMR spectra, lot of molecules, and also further I showed you what happens when there is a complexity. We can do the decoupling. Selectively we can decouple particular nuclei and simplify the spectrum to get the coupling information. With all those things, I think we have got sufficient information, and I exposed quite a bit about the analysis of the spectra of proton, so that you are now going to be very comfortable in getting the information. Now, we will go further today and start working on carbon-13 NMR spectral analysis. We will look for carbon-13 NMR. Of course, carbon-13 is another NMR, another nuclei, which is extensively utilized, especially by organic chemists, because in most of the organic molecules, carbon is invariably present. When I talk about the carbon, we have several isotopes of carbon. Carbon-12 and carbon-13 are naturally occurring, that is important for us. Carbon-14 is radioactive, we do not have to worry about it. And if I look at the natural abundance, carbon-12 is 98.9% abundant, whereas carbon-13 is 1.1% abundant. Very interestingly, the spin for carbon-12 is 0, that means carbon-12 is NMR inactive, whereas carbon-13 with a spin half is NMR active. And this is very important thing for us, because if carbon were to be 100% abundant, then our proton spectra in many of the organic molecules would have become extremely complex to get the information. So, nature has in a way helped us, so that by making carbon-13 abundance 1.1%, and though it participates in the coupling, but it does not complicate the proton spectrum. So, okay, these are the general information. As far as the salient points of the carbon-13 NMR is concerned, what are the factors which affect the chemical sheet of protons? We analyze chemical sheet of proton spectra. There are several factors, I said steric factor, isomeric effect, and also the electronegativity substituent, aromatic ring current, varieties of factors contribute to chemical shifts. All the factors which affect proton chemical shifts also affect the carbon-13 chemical shift. That is another important point. So, that is the thing we should remember. And the chemical shifts we are going to reference it with respect to tetramethyl in proton. Same reference is used for carbon-13 also. And interesting point we should know is, we discussed this when we explained about the chemical shift. Resonating frequency of protons is 4 times more than that of the carbon, or in other words, resonating frequency of carbon is 4 times less than that of the proton. Meaning, if I have a NMR spectrometer which is resonating at, let us say, 200 megahertz, where does proton resonate in that spectrometer? I mean, where does carbon resonate? Carbon resonates at 50 megahertz. If the proton is resonating at 200, carbon is 1/4 smaller than that, because carbon gamma is 4 times smaller than that. This also we discussed extensively even in the first or second class itself. Okay, now coming to the chemical shift range of carbon-13 NMR spectrum. Like proton we discussed 0 to 10 ppm is the general scale, and I also said it can go beyond DTMS and also beyond 10 to 12 or even 15-20 ppm in extreme cases. But by and large the range of chemical shift of proton is fixed, it is between 0 to 10 or 12 ppm. Then what is the range of chemical shift of carbon-13? That is 0 to 300 ppm with respect to TMS. That is the range of chemical shift of carbon-13. And like we have seen, like different functional groups, where do they resonate in the proton spectrum? Similarly, like where do they resonate in the proton spectrum, there is also the table which is given. In this chart you can see different functional groups, where do they resonate. For example, if you have an aromatic, it may come around let us say 100, 120, 130 ppm. Aliphatic CH3, CH2, CHS will come from 0 to 40 or 50 ppm, like that we know. Exactly whatever you see in the case of proton, same thing can be more or less translated to carbon-13, with of course slight modifications could be there, but not extremely different. It is more or less you can translate the chemical shift information what you do for proton also to carbon-13. And of course, salient points for carbon-13, if you look at it, one thing is always carbon-13 spectra are obtained with what is called broadband decoupling of protons. When we look at the carbon-13, usually all the protons that are coupled to carbon are completely broken. No coupling information will be there. We will remove the coupling of all protons to all the carbons. This is called broadband decoupling. This is a very important point, otherwise spectrum would have been very complex. The result of that is each peak is corresponding to a individual carbon, chemically inequivalent carbon present in the molecule. So, if I have 10 peaks in the NMR spectrum, carbon-13, there will be 10 carbons in the molecule, that is all, very easy. Each peak identifies a particular carbon in the molecule because of broadband decoupling. And a few continuing further, the number of peaks always indicates number of chemically inequivalent carbons in the molecule. For example, there may be 10 carbons, but you may get 8 peaks. That means there are only 8 are chemically inequivalent. 2 of them somehow have chemical equivalence and they will be overlapping. So, number of peaks tells you, similar to proton, number of peaks in the carbon-13 spectrum tells you number of chemically equivalent carbons present in the molecule. One point you must always remember, I said all protons are completely broadband decoupled from carbon, that is fine. We are removing only carbon proton couplings, but we are not removing the couplings of carbon with other heteronuclei. That couplings are still reflected in the spectrum. Of course, nowadays in the present day spectrometers, you can do the decoupling of 2 nuclei, 3 nuclei at a time. That is a different question. But by and large, generally, when you record the carbon-13 spectrum, all protons are decoupled, whereas coupling of other nuclei with carbon are still present. That gets reflected in the spectrum. With this, let us now talk about the sensitivity of carbon-13 relative to that of proton. We already discussed about the sensitivity. I told you gamma of the carbon is 4 times smaller. As a consequence, energy separation is 4 times smaller, and I correlated this energy separation with the population using the Boltzmann distribution. I told you earlier that means the population difference between two energy states is much smaller here. As the energy separation becomes more and more, population difference becomes larger. That is what I said. So, as a consequence, its sensitivity is less, 4 times less. But I also said gamma depends upon 3 other factors. It is gamma cube. It is 4 cube. So, as a consequence, what is going to happen is, if you go to the sensitivity of the carbon-13 relative to proton, when proton resonates at 800 megahertz, carbon resonates at 400 megahertz, and the energy gap is 4 times smaller, sensitivity will be 4 into 4 cube plus is 1% abundant less compared to that of the proton. So, as a consequence, it turns out to be 5672 times less sensitive compared to that of proton. Remember, if I have a sample, all keeping every parameters all identical including relaxation time, varieties of things, if I take 1 minute to get a proton spectrum, in reality, assuming that everything remains same, I must take 5672 time. That is much more, very time consuming. That is because the sensitivity of the carbon is much smaller. In fact, if I have to get the signal to noise ratio, I have to take the square of this number 5672 into 5672. As a consequence, it is really time consuming. Sensitivity is very low. Carbon-13 NMR is that way more time consuming than proton NMR. Please remember this point. With this, I want to introduce one parameter which already I discussed indirectly or directly in some 1 or 2 classes. We have to talk about isotopomers of the molecules. Let us consider an example of CH3Cl. CHCl3. In CHCl3 there is only one carbon, and carbon has 2 isotopes already I told you, carbon-12 and carbon-13. Carbon-12 is 99% abundant, carbon-13 is 1% abundant, that is what I told you. That means if I have 100 molecules, only one molecule will be like this with carbon isotope as present as carbon-12. 99 molecules will be present as carbon-12 present as this molecule present with carbon-12 isotope, whereas only one molecule will be present as carbon-13 isotope. Remember, 99 molecules will be carbon-12, or in the carbon-12 state only one molecule has carbon in its carbon-13 state. Okay. So, if I consider isotopomers when 2 carbons are present in the molecule, let us consider the example. Instead of single carbon, let us say what happens if I have 2 carbons present in the molecule. We can think of possible combinations. There is a possibility. I am taking a hypothetical molecule, do not worry about other substituents of this molecule. Hypothetical molecule with the 2 carbons chemically inequivalent bonded by a single bond like this. There is a possibility and large possibility that this carbon both can be in carbon-12, but probability is more because each carbon has 99% abundance of carbon-12. This also 99% abundant, and the possibility of this is 97.8% of the time you will have this type of molecules. Unfortunately, such molecules are NMR inactive. It will not give spectrum for you in the NMR spectrum. So, but unfortunately they are present in the large quantity in a given molecule. This type of isotopomer is present almost 98%. Now, think of other possibility. One more possibility is this carbon can be carbon-13 and this can be carbon-12. Okay. Then what is the probability? Only 1.1%, and this is NMR active spin. Think of the other possibility. This is carbon-12 and this is carbon-13. What is the probability of seeing this? What is the abundance of this? only 1.1% carbon is abundant. This is anyway 99% ruled out. So, it is 1.1%. This is also NMR active. What is the last possibility you can think of? Both the carbons are present as carbon-13. What is the probability of seeing both the carbons present as carbon-13 in the molecule? Each one has a probability of 1 over 100 because it is 1.1% abundant. Forget about 1.1, make it 1%. So, it is 1 over 100. The probability of both of them present jointly, simultaneously as carbon-13 is a joint probability. It is 1 over 100 into 1 over 100. It is 1 in 10,000. That means NMR percentage of abundance of this type of molecule is 0.000121%. But this is NMR active because both are carbon-13. And such type of molecules are extremely difficult to detect because this is already in abundance is so small and this joint probability is 0.000121%. Extremely difficult to see such molecules and get the spectrum from such molecules. So, when there are two carbons present, already you have a lot of complications. Complexity is more. Let us go further. What happens if there are 3 carbons present, all the 3 in carbon-13 state? Think of a situation. Probability of all carbons simultaneously present as carbon-13 is 1 over 100 into 1 over 100 into 1 over 100, which turns out to be 0.501331. Look at it. This is a very, very small number. 0.501331 is coming into the picture. And nearly this is 1 in a million. If there are 1 million molecules present in your sample, there is only one molecule. The probability you will find is only one molecule where all the carbons are present as carbon-13. Extremely difficult. Forget about it. Now, let us go to a complicated situation. In a given molecule, there can be organic molecule consisting of large number of carbons, 10 carbon, 15 carbon, 20 carbons, like that. Take another complex example where a hypothetical molecule like this, there are 6 carbons present here. I have deliberately chosen this. What is the probability of seeing all the 6 carbons in carbon-13 state? All carbons being in carbon-13 state. What is the probability? That is 1 or 1 10 to the power of 1 in 10 to the power of 12. 1 in a quadrillion. Imagine such a very, very, very small number. Almost 0.8 or 10 zeros followed by this one. That means 10 to the power of 12 molecules if they are present of this type of molecule. Only one molecule you can find which has all the carbons present as carbon-13. How can you see that? In 10 to the power of 12 molecules, only one. Already 10 to the power of 23 is Avogadro number of molecules. If you take Avogadro number of molecules, maybe 1 or 2 molecules will be there. How can you see a signal from such a thing? Extremely difficult. Very, very. NMR is basically insensitive technique. And if you have abundance like this, how can you see that spectrum? It is really a very, very difficult situation, and practically it is impossible to see the carbon-13 spectrum of such big molecules where all the carbons simultaneously present as carbon-13. Very difficult, practically impossible to see. Then the question one can ask, how can we see all the carbon peaks in a molecule containing large number of carbons? Theoretically I showed you it is difficult, but practically we are seeing the spectrum. Go to take any organic molecule containing large number of carbons, 10 or 15 carbons, no problems. Go and take the NMR spectrum, you will get it. Then how can we get that? I just now said even with 6 carbons is 1 in a quadrillion. But how can we get the spectrum of a molecule, where carbon-13 spectrum of a big molecule containing large number of carbons? How all the carbons can be simultaneously present as carbon-13, which is impossible. Extremely, not impossible, it is extremely difficult to see, very, very, very low possibility. The question is, we will understand that now. How? This is the important point which you must know, carbon-13 spectrum, how we get it. Because this concept is another important part of this course. Before going further, let us try to understand how does protons attached to carbon-13 influence the carbon-13 spectrum, assuming we are not doing any decoupling. If I have a molecule like this, a CH3 group is present, if all the 3 protons are chemically equivalent coupled to carbon-13, then what is the pattern we get for carbon-13? Remember, carbon-13 is a different nuclei, protons are different nuclei. When these two can couple to each other, these are all magnetically equivalent, are chemically equivalent, doesn't matter whatever you take. When this coupled to carbon-13, what is the pattern you expect? Same 2 Ni plus 1 rule, it should give rise to 4 lines, 4. So 2 into Ni plus 1, you put it 2 into 3 into half plus 1, you are going to get 4 peaks. And according to Pascal triangle, the intensity pattern is 1 3 3 1. That is what we should get. So CH3 carbon, if you look at it, when the protons are coupled to carbon, you get a quadrat with intensity ratio 1 3 3 1. What about CH2? You can think of a situation like this. 2 CH2 carbons are coupled to 1 carbon, CH2 protons, you are going to get a triplet. As usual, like a CH2 proton coupled to CH3 makes it a triplet. Here 2 protons chemically equivalent coupled to carbon makes it a triplet, 1 to 1 intensity. Next, go further. If I have only a situation where only 1 carbon is there which is coupled to only 1 proton, what is the pattern you expect? This is only 1 proton, obviously it is like AX spin system. This carbon will be a doublet. That is what you are going to see. Go to a situation where there are no protons attached. There is no coupling of carbon with proton at all. They are called quaternary carbons. Each carbon has 4 carbon bonds, none of them are attached to proton. They are called quaternary carbons. Such carbons give only a singlet because there is no coupling with protons. So please remember, if I look for the carbon-13 coupled spectrum, CH3 group gives a quartet, CH2 gives a triplet, CH gives a doublet, and a quaternary carbon gives a singlet. With this knowledge, take an example like this, a hypothetical molecule. If I have a molecule like this, you will simultaneously, if you take the record the spectrum of this molecule, you will get a quartet for this, triplet for this, doublet for this, and singlet for this. Hypothetically, I have written this molecule just for you to get the feeling. You understand how the multiplicity of the carbons are there when they are attached to a different number of protons. Different group number of protons when they are attached, this is what happens. With this knowledge, let us try to understand the carbon-13 NMR spectrum of ethanol. Very simple molecule. Ethanol has 2 carbons, carbon CH3 group and CH2 group. How do we get the carbon? First of all, let us understand isotopomers of this isotopomers of ethanol. How many isotopomers of ethanol you can think of? 1 with both the carbons are carbon 2, that is what we said. In a molecule containing 2 carbons, our probability is 97.8%. You will not get spectrum from this ethanol at all, this molecule. You will 98% of the molecule will not give you any NMR signal. Okay, forget it. Come to other molecule. This CH3 can give a peak 1.1% NMR active. See, this carbon-13 spectrum can be obtained because of this CH3 group. Go to this situation. This CH2 carbon will give a peak, but this will not give me the peak. Again, this is only 1% active, 1% possibility. Go to a situation like this. Probability when both the carbons are present simultaneously as carbon-13. I told you this is probability is 0.000121 NMR active, but this is very difficult to see. The signal from this isotopomer is not easy to detect, very difficult to detect. So we will forget about this because it is anyway difficult to detect. So we have to worry about only these things. We have to worry about only these two groups, these 2 molecules. Anyway, this is NMR inactive. So what we will do is we will not worry about first molecule, we will not worry about last molecule here. We will only worry about only second and third molecule. How does the spectrum carbon-13 spectrum come? We will see. Already I told you, when carbon is coupled to proton, 3 chemically equivalent, when I take this molecule, I am going to get only a quartet, that is all. This carbon is not contributing, this is one isotopomer. Let us think of other isotopomer. Of course, this separation corresponds to this one bond carbon proton coupling. Let us consider other isotopomer, where this is, I am sorry, this should have been 13, this is 12, it is a mistake. This should have been carbon 13. CH2 is carbon 13, this CH2 carbon, in which you are going to get a triplet here. So, what is the separation? This is one bond, this carbon proton coupling. Okay, this is one bond, this carbon proton coupling. This anyway will not give you the signal in this isotopomer. You understood? Now, for two isotopomers, I got two different spectra. For this isotopomer, I got a quartet, and for this isotopomer, I got a triplet. But in reality, in a given sample, you do not have only these isotopomers and you do not have only these type of isotopomers. Everything is simultaneously present. All 4 types of isotopomers are present. First one you ignore, last one do not give signal, very difficult. Only these two will give the signal. So, in a given sample, because all the molecules isotopomers are simultaneously present, only these two give the signal. Okay, let us worry about these two. Then you may ask me a question, what about long range carbon proton couplings? For example, you consider a situation like this. When I am looking at this carbon, I look for only one bond coupling with proton. Since I am not decoupling, what stops me in telling this proton also can couple to this carbon? Possible. It is possible, it will couple. So, in reality, you will have the spectrum, one bond coupling of this carbon to this triplet, this here 3 protons will give you a quartet. But at the same time, these 2 equivalent protons, CH2 protons, they will split each line of the quartet into triplet. Remember, we understood the multiplicity pattern earlier. So, what is the type of spectrum you are going to get for this molecule? You are going to get CH3 carbon will be a quartet, and each line of the quartet will be split into triplet because of HH coupling, CH3 proton, CH2 proton coupling. So, you will get 1 bond CH coupling and 3 bond this carbon and this proton coupling. Okay, not HH coupling, CH coupling. 1 bond CH coupling and 3 bond CH coupling you are going to get. This is the thing you are going to observe. Go to this molecule. What is the pattern you are going to get for this one? I told you, you will get a triplet because this carbon is coupled to these 2 protons and becomes a triplet. But this carbon can also couple to this proton. What stops us from preventing this proton coupling to this carbon? Long range proton carbon couplings are present. Then in reality, there is a 1 bond coupling and also 2 bond or 3 bond coupling of these protons to this carbon, that is also possible. So, CH2 carbon will be a triplet because of direct protons coupling, 2 protons, and each line of the triplet is split into quartets because of coupling of CH2 carbon with CH3 protons. So, there is 1 bond carbon proton coupling plus 3 bond carbon proton couplings, both are present. So, what is the pattern you are going to get finally? When of course, this one you do not see, you can ignore it. But remember that coupling exists. What C13 coupling? We do not see the spectrum of the molecule, but that does not mean you do not have the molecule, you do not have the coupling, it is there. Molecules are also there, coupling is also there, but very difficult, we do not detect it, that is all. So, what about the proton-proton couplings? That is also possible. But remember, when you are looking at the carbon coupling, carbon spectrum, carbon proton couplings are seen, 1 bond carbon proton and 3 bond carbon proton couplings. But proton proton coupling, CH3 protons and CH3 protons coupling, you will not see. Why? Protons are passive spins. I told you already, passive couplings are not reflected in the spectrum of active spins. Active spin here is carbon-13. So, at this carbon-13 resonance, when you are looking at it, proton-proton couplings are not seen. So, you do not have to worry about it. So, in reality, all spectrum of isotopomers are there, first one do not give, remaining 3 are there, last one is not seen. So, the total coupled carbon-13 spectrum of molecule of ethanol is the superposition of the 2 spectra. 2 spectra coming because of 2 isotopomers. If you look at the carbon-13 spectrum, 1J CH couplings, CH3 will be a quartet and CH2 will be a triplet. But there is also a long range coupling, long range 3 bond CH coupling, which makes this as quartet, triplet of quartets. This will become quartet of triplets. This is the complexity of the spectrum you get. In reality, if you take the fully coupled proton carbon spectrum, this is what you are going to get. But what we are going to do, generally, beginning itself I told you, all the carbon spectra are recorded with broadband proton decoupling. That means all this HH coupling, CH 1 bond, 3 bond HH, CH coupling, not CH couplings, will be completely removed. So, in reality, this is a coupled spectrum, but what we get every day when you record the spectrum is like this, 2 peaks, one for this, one for this. Basically, we have reduced this complex multiplicities pattern into a singlet. Similarly, all this complexity will disappear and give a singlet. So, you are going to get 2 peaks for carbon-13, one for CH3 carbon, one for CH2 carbon. See, it is an ethanol molecule, but what do you understand from this? What you understand from this is, for a molecule with n chemically non-equivalent protons and n chemically equivalent carbons, n chemical non-equivalent carbons, the proton detected spectrum is from a single molecule, where all are 100% abundant. Whereas, for a molecule with n chemically inequivalent carbons, n isotopomers are there, each with a different isotope. There will be n spectra, each with a different isotopomer having carbon in different state, carbon-13 state. So, for example, I have n isotopomer. Each isotopomer will have one carbon in carbon-13 state. So, if there are n isotopomers, you have n spectra overlapped. So, carbon-13 spectrum is the superposition of spectra from n isotopomers. Please remember, when you record the spectrum of any given molecule, the proton spectrum is from a single molecule, but the carbon-13 spectrum is not from a single molecule. It is the superposition of the NMR spectra from all isotopomers present, n different types of isotopomer, which give rise to carbon-13, detectable carbon-13 spectrum, and that is what it is. And this is a simple example to show in a diethyl phthalate we have CH3 group, CH2 group. Okay, this takes some more time to explain. What I am going to do is I will stop here. I will come back and discuss this in the next class. But so far what I was trying to tell you today is to introduce the carbon-13 NMR, which is one of the exotic nuclei which is used apart from carbon by most of the chemists, and I gave you salient features of carbon-13. Sensitivity is much low compared to proton, and resonating frequency is 4 times smaller than that of the proton. Always carbon-13 spectra are recorded in the broadband proton decoupled state, in which case each carbon chemically inequivalent present in the molecule gives only one peak. If there are n peaks in the carbon-13 spectrum, there are n chemically inequivalent carbons present in the molecule. That is what you should understand. And then I also said, if I have a molecule with n protons, the spectrum are n chemically inequivalent protons, the spectrum is from a single molecule. Whereas, if there are n chemically inequivalent carbons present in that, spectrum is not from a single molecule. Spectrum, carbon-13 spectrum is the superposition of the spectra of n different isotopomers, where carbon-13 is present in different places in each of these isotopomers. And that is the summary which I wanted to tell you. We will continue with this further discussion on carbon-13 in the next class. Thank you very much.